One of the problems in class that we have a difficult time with involves non-conservative work. And really, it's not too hard if we just look at it the same way we do other problems. And so one of the things that we do with non-conservative work is we typically act like there's a constant frictional force. And the first thing I guess we need to talk about is, what does that mean? If we have an object like this that's going to go down the incline, and we look at it, the slope of the incline will change, obviously, throughout. That would also change the friction force along these paths. And the easiest thing, I think, to do in the problems to make it a little bit more straightforward is just to say there's a constant friction force. And so a lot of times, even though our friction would change, we kind of ignore those things in class. Now, I'm not saying we can't do problems involve something like this or something with just a straight up incline, but we tend to not do those things. And for this test that we will have in our class, we won't. So this problem will focus mainly on trying to figure out how far an object will go before it stops, and maybe the friction force involved. All right? So let's imagine we have a flat surface and we have a mass, and the mass is going to start with an initial velocity of, let's say, 10 meters per second. Okay. And let's give this mass of an object 1.5 kilograms. I don't know how much a hockey puck actually has as far as the mass, but let's imagine it's like a hockey puck. So you slap it with the stick and it's moving. Well, even a hockey puck, given enough time, will come to a complete stop. Let's say in our problem we have a constant friction force of 0.75 newtons. So the question that will arise is, okay, how long does it go before it stops? So ultimately what we're finding is the x. And we'll say that at this point the velocity is equal to 0. Okay, so we have a puck or some kind of object, we hit it, we kick it, we push it, and we let go, and then sooner or later it will come to a stop. So the first thing that we should do is always ask ourselves, okay, what kind of energy do we have here at the beginning? And we would realize that we have kinetic energy, initial. And then the next question is, what do we have here at the end? And this is where students get sort of stuck because they're used to having it moving or maybe up an incline. And the fact is the velocity is 0. So we know that kinetic energy is 0. And we also know that it's not off the ground, so there's no gravitational. And so what do we have? All we have is the non-conservative work done. So it's the work done by friction to actually stop it. And so we set those two things equal. And I'd like to say, and you've heard me say this before, that this is the real physics. Understanding and figuring out what two things are going to be set equal, what two energies are going to be set equal. And so I'm going to try to find what this x is right here. Where is it? Is it going to be in the KE or the WNC? It's going to be over here. Okay. It's the friction done over that displacement. So kinetic energy is 1/2 mv squared. That's the initial. Friction force times the displacement. If I solve for the displacement, we would get 1/2 mvi squared, I forgot the squared, divided by our f. And you could check this and you could plug all the numbers in. Okay, our mass would be 1.5. Our velocity would be 10. We have to square it. All divided by, right here, our friction force. And we multiply it out and we get an answer. I'll do that now. 0.5 times 1.5, I shouldn't even plug that in, times 100, that's 10 squared, 100, divided by 0.75. Oh, look at that. Amazingly, we would get 100 meters. So this would actually travel, it looks like, from the end of one end zone to the end of another end zone on a football field. So that's pretty far. Okay? And if we think about a hockey puck, how long would that go before it stops? Well, that might be pretty reasonable. All right? So that's one of the simple types of problems. In another video, I'm going to show maybe a little bit more involved, maybe one that involves an incline and some other roller coaster type things, okay? So a quick review. When the object totally comes to stop, why does it happen? It happens because of friction. And whenever you have friction, you're going to have this non-conservative work done. And we ask ourselves the same two questions we always do. What is the initial energy that we have? And how about the energies at the end? And we set those two things equal. Hopefully this won't show. Okay, so in the first video, I showed you how to find how long it takes an object to stop, so the displacement when there's a friction force. In this video, we're going to talk about finding the friction force, okay, giving maybe some other types of problems where maybe we're not on a flat surface, hey, maybe we are. Okay, so let's say we have a roller coaster, kind of like this, okay? And we're going to say that the height of the roller coaster is 200 meters. Right, 3 significant figures there. And we're going to say that the total length of the roller coaster, and I got to tell you right now, I'm just making this number up. The total length is going to be, let's see, $3,000 meters. Now I know I showed the vector sign over the x, and we have this kind of curly Q thing down. All right. Now, if anybody's watching this problem and they want to say, well, this isn't exactly correct. If you watched the first video, you would hear me talk about how the friction force is going to remain constant, at least for our problems right now. And so even though the friction force would change, you know, if you're on an incline, it would be less. If you're on a flat surface, it would be more. Even though that would change, we're going to say that it stays constant throughout the whole thing. Okay? So if you want to, you could even imagine it being a nice little gliding, kind of sloping down. And we're going to assume that this roller coaster can do anything. It can do curves, whatever, that the friction force is going to stay constant the entire time. Okay? Let's put an object at the top, and we're going to have a mass of 200 kilograms. And I want to find how much friction. And so our parameters are kind of like this. What we're going to say is the object starts to go down, and then it comes to a stop right as soon as it pulls back into the bay that that you leave from, so the starting point. All right. So it's a little bit different. Hopefully we're following what's going on. Okay, so here's my problem setup. Okay, so hopefully you watched the first video on non-conservative work and the first problem. What's up?
Not much. I'm doing a favor for a friend right now.
Okay.
I'm sorry if I'm interrupting.
Yeah, you are. That's okay.
This is Eric's.
Are you serious?
Yeah, he actually.
So he's gonna come eat it.
Because he's making up a test during his
Yeah, yeah, he told me. Perfect.
Sorry.
No, you're fine. Thanks, man. Thank you. Eric. All right, so hopefully you watched the first video where I talked about non-conservative work and finding the friction. In that first video, we actually found how far the object would travel before stopping. And in that video, I talked about how we're going to say that the friction force is going to be constant. Okay? What does that mean? Well, it makes our problems quite a bit easier. So let's say we have this setup, and it's a roller coaster, and it's a really simple one. We say that we start at a place and we stop at a place, and we're given some energy at the top of the first hill, and then the energy, gradually dissipates because of friction, and then the object comes to a stop just perfectly right as it pulls back into the starting place so that people can get back on. Or get off and get on the roller coaster. And we're going to say that our first hill is 100 meters high. We're going to say the mass of the cart is 200 kilograms. And we're going to say the total length of the track is 300 meters. Now, I know, if you go around and you come back and you start in the same place, the displacement would be 0. So maybe we could think about this as just a long, straight track. Okay? For what we're trying to do, it serves us pretty well. Okay, and we're trying to look at maybe some potential energies and non-conservative work and those sorts of things. And so let's go back to the first two questions we ask ourselves. What energy do we have at the beginning? What energy do we have at the end? And so right here at the beginning, if we're on a hill, we would have the potential energy due to gravity. Now the one thing that we're going to say is that the object just like barely gets started, so there's no kinetic energy involved. And then at the end, we're going to say that it stops completely. Okay? And so we're going to say the velocity is 0. And if the velocity is 0 and we're totally at the bottom of our track, we know that all we have is the non-conservative work. And so if we look at this and we want to try to figure this out, we would say the potential energy due to gravity initial is equal to WNC. Right? My non-conservative work is the friction times the x, and ultimately I'd be solving for this F, and we can do that. And I think if you look at the other problem, you'd be able to do this. mgh equals Fx, and then you just go ahead and you solve for F. All right, so let's change the problem a little bit. Let's say that you come into your final position here at the end, but the cart's still moving. So instead of saying 0, we're going to say, it comes in with a velocity of 2 meters per second. So what do we do now? Okay, well, I still have the potential energy at the beginning, And at the end, I'm going to have now kinetic plus all the energy that we lost, W and C. So it makes it a little bit more difficult, but hey, you know that if it's moving, it has kinetic energy, so just go ahead and add that on. So let's go ahead and solve this. PEG I equals the kinetic energy final, right? This is final, plus W and C. And what are we looking for? We're looking for the friction force. All right, so the potential energy is mgh 1/2 mv squared plus our friction force times our x. All right, I'm going to solve for x is equal to mgh minus 1/2 mv squared. Now remember, when we talk about the v, we're talking about the final velocity. We're going to divide that by f. You could check that algebra out, make sure it makes sense and that it adds up. When we put our numbers in, and that's something I'm going to leave it for you to do, our mass is 200, our gravity is 9.81, our height is 100, our final velocity is 2, and our constant frictional force is what? What are we solving for? Oh, I guess I made a little mistake there. So after that first problem, I still had in my head that we're solving for the x. But actually, in this case, we're solving for the frictional force. And so we divide by the change in x. Right? So it wasn't too bad of a mistake as far as this goes, because we would just divide out the f or divide out the x here, depending on which one we're solving for. Right? So that was a mistake, obviously, on my part. But if you were to go back and look, you would look and say, well, hey, I don't have the frictional force, so what do I do? And that should have been a little bit of the thing that you noticed and kind of like told you that you were wrong. Your mass is 200 times 9.81 times 1,000 minus 0.5 times our mass of 200 times 2 squared right here, and I'm going to just put in 4, divided by our x, which is 3,000. And I get this frictional force of 653.9 newtons. If I look at the significant figures, it looks like we have 2, so 650 newtons. So that friction force is pretty high. The numbers were just made up as far as this 3,000 meter track. I bet you tracks are a lot longer than that, which would decrease our friction force quite a bit. All right, but the general idea of what you need to set equal would remain the same regardless of what numbers we put in. Okay, the idea that we need to figure out energy beginning, energy end. Okay, and if we have some movement at the end, we need to add in this kinetic energy, and then we add in the energy lost, which is our work non-conservative, which is the work due to friction. All right, so hopefully these problems aren't too difficult. They should be the same as the conservation of energy problems, and just adding this little W on here. The one thing you'll notice that whenever it seems like we have our conservation of energy problems without springs, okay, we don't need the mass. Okay, if we put springs involved, we need the mass. If we have non-conservative friction involved, we need the mass. Okay, so if you're not given the mass, make sure that you're looking at the problem correctly and whether it has friction or not. But definitely when you have friction, you need this mass.